excuse me. So we'll see now the next application. It's has to something to do with proteins. So proteins, they form complexes. So no protein, a single protein doesn't really exist. So it's a complex. Okay, and proteins, if you know, are basically they compose a lot of amino acids. So amino acids have kind of some chemicals, okay, that will try to bind to each other. So a protein, there is a protein synthesis process. Is how is protein created is forming in your body. So that's called protein synthesis. So at the time of its synthesis, it may exist like a chain of amino acids like this. So it's like a linear chain. But then once it has completed the evolution synthesis process, the amino acids try to link to each other. So this protein is like a chain of amino acids containing two or more. So then once the protein is formed, the amino acid chemicals will try to bind to each other, and that will lead to a three-dimensional complex of all the amino acid involved there. So that's what is called as a protein complex. Okay. Now, how folded is a protein is what we want to quantify. Okay. So how can we do that? So we can model a protein complex as a graph like this, where each amino acid is like a node, and there's a link between two amino acids if the two amino acids have some bonding with each other. And at the minimum, you can have a chain of amino acids like this without any binding. So it's just a chain. This is a binding, but that's the minimum you need to have a connected set of amino acids to form a protein. On the other hand, you can have a complete graph of amino acids in the sense that there's a link between any two amino acid that is part of this complex. So that's the best level of bonding we can have. So these are the two extremes. One is a chain, and the other is like what is called a complete graph. Okay. So given an arbitrary graph like this, we want to be able to quantify or find out where this graph stands in between these two extremes. Especially we are interested with, related to this complete graph, because this is the best thing we would like to have. Okay, a three-dimensional complex that is having all this lot of binding inside this complex. So how close is our graph to this complete graph of the vertices? So that's what we want to quantify. And there was a well-known researcher. He is known for a lot of research in eigenvalues and spectral analysis, called Estrada, and he did this work and came up with what is called this Estrada Index to quantify the extent of protein folding. Okay, so the idea is to compute the eigenvalues of a given graph, again using the adjacency list or matrix, and then use this formula, which is find e to the power of these eigenvalues. So you're going to have 5 eigenvalues for this 5 vertices graph. So compute e to the power negative 1.618 plus e to the power negative 1.473 plus e to the power negative 0.463 and so on, and these are the corresponding numbers, and sum up all these e to the power lambda values, and that's the kind of this what you can call as the raw value of Estrada Index. Okay, but as I always say, when you quantify something, it's always better to put it in a scale so that we can get of an idea of how large or how good is the property is that we are trying to analyze. Like in the previous two cases, that's what we did. The spectral radius ratio of node degree, I said the closer it is to 1, the less the variation in node degree, and farther it is from 1, the more variation in node degree. And for bipartite index, I also said it could go all the way to 0.5 and then as large as 1. So the more closer it is to 1, the more closer is the graph to being a bipartite graph. And the more, the farther away from 1, so you can think like that. The farther away is the bipartite index from 1, the less the bipartite nature of the graph. So that means you're going to have more frustrated edges in the two partitions. Okay. So again, for any graph you could come up with two partitions, but using this approach, if you try to find the two partitions of the graph, you are going to find the optimal partitioning of the graph into two partitions, such that you are going to have as few frustrated edges as possible between vertices in the same partition. So that's the specialty of this approach, using eigenvalues and eigenvectors. So if you use the lowest negative eigenvalue and the corresponding eigenvector to identify the two partitions, you are going to get the best partitioning of this graph to two partitions, such that the number of frustrated edges involving the vertices in the same partition is going to be as low as possible. So the bipartite index measure again is in a scale of 0.5 to 1. So using that, you can get an idea of how close the graph is to be bipartite. So now, with this raw number, we cannot visualize such a thing, because for some other graph it could be 400. Then that doesn't mean that the graph with 400 as a sum of its eigenvalues has a relatively more folding compared to this graph. It depends on the number of vertices in the graph too. So again, we want to make this metric, the quantifiable metric things that we come up with, like spectral radius ratio or bipartite index, to be independent of node degrees. Like it doesn't really depend upon the bipartite index, doesn't really depend on the number of nodes. It could be a graph of 10 vertices or it could be a graph of 6 vertices. Still, we could measure the bipartite index on a scale of 0.5 to 1. So that is something like we would like to do in each of the metrics that we would like to develop in this area. Okay, so make it independent of the number of nodes. So how to make this Estrada index also independent of the number of nodes? Now, one idea is this. So since we would like to have a complete graph of the vertices, so if you are given this graph of 5 vertices, try to draw a complete graph of these 5 vertices. So a complete graph means a graph in which every vertex is connected to every other vertex. So 1 is connected to all the other 4 vertices, 2 is connected to all the other 4 vertices, 3 to the other 4 vertices, and so on. So the corresponding matrix will look very simple like this. So all entries other than the diagonal are going to be 1. You could use that to feed into an eigenvector program, or you can type that as a list. So 1 is connected to 2, 3, 4 and 5. That means 2 you have to say is connected to 3, 4 and 5, because 2, 1 is already written here. Similarly, 3 is connected to 4 and 5, then 4 is connected to 5. So this is the adjacency list for this complete graph. And if you find the eigenvalues for such a graph, it will come out to be something like this. So the largest eigenvalue, in this case 4, is actually 1 less than the number of vertices. Okay, and the others are all -1. So that's another characteristic. If you have a complete graph, these are the eigenvalues you're going to get for a graph, for such a graph. If you find e to the power lambda, or e to the power of these eigenvalues, the last one, since a very large integer number, e to the power of that is going to be even larger, like 54.576. So if you sum up all these things, the sum of all these e to the power lambda values will be closer to that of the largest eigenvalue, like what you got for just based on the largest eigenvalue. So you get 56.048, which is reasonably close to 54.576. So now this is what we are going to do. Once you get this number 56.048 for a complete graph of 5 vertices here, we can divide this ratio, so I'm showing here, so we can divide that ratio 21.56 and divide by 56.048. So this ratio is called the folding effectiveness. Okay, so the Estrada Index, which is the raw Estrada Index for the actual graph given to you, divided by the Estrada Index for the complete graph of the same 5 vertices, can be called as the folding effectiveness, okay, the ratio. So the more closer it is to 1, the more folded is the protein. So that means the more edges you are going to have between these vertices. At the best case, you could have all edges between all possible combinations of vertices. That would lead to a complete graph like this. Then the ratio will be 1. If you don't have a complete graph and you are missing some edges among the vertices, like this graph, you are going to get the ratio to be less than 1. So the more closer it is to 1, the more folded is the protein, and vice versa. So for this graph, again, the eigenvalues came out to be what I have here. So these are the eigenvalues. And the sum of these e to the power lambda of these eigenvalues comes out to be 16.51. Now you can see here, unlike a complete graph, it's not just the largest eigenvalue that is making almost the entire contribution to the sum. The other eigenvalues, especially the next largest one, is also making a reasonably good contribution to the sum of the eigenvalues. And that's what you expect to see in a real world graph that is not complete. The eigenvalues other than the largest eigenvalue will also make some contribution to the sum of the e to the power lambda values. And you can also see that the less complete as you go. So this is like a chain, and these are the lambda values. And e to the power lambda values, you can see even smaller lambda values are making a reasonably good contribution to the sum of the eigenvalues. Okay, so the sum of the eigenvalues is farther away. It's almost like just close to 1/2, as close to double the largest the e to the power lambda value corresponding to largest eigenvalue. So on the other hand, if you do it for a complete graph, you see the largest eigenvalue makes almost the entire contribution to some of these e to the power lambda values. Okay, so that is another property. So that means the ratio will go down as you go more toward a chain of the vertices compared to a complete graph. Okay, so that is something you need to know about this folding effectiveness, and is used for protein analysis to quantify the extent of protein folding. And I was talking about the eigenvalues. I was thinking about this property which I did not think I mentioned here. Now again, one more thing you can say about a bipartite graph is this. So we're looking at, say, a graph that is bipartite and the eigenvalues of a bipartite graph. So the eigenvalues of a bipartite graph has a very interesting property. You notice that the sum of their sin h values were 0, right? Because this graph was a truly bipartite graph, and the sum of the sin h values were 0. You can notice here, as well as in the other example that I was about to show, the eigenvalues for truly bipartite graph. That means that there are no frustrated edges. It's a truly bipartite graph. So the eigenvalues are going to be like mirror images of each other. So you put a mirror in between the negative and positive values, you are going to just get the absolute values of those negative values on the other side. So for this negative one, you are going to have this positive one. For this negative one, this is positive 1, and for negative 2, it is positive 2. Now let us go back to this case. For this is a graph of 6 vertices, an even number. So we're going to have 6 eigenvalues. Now you have 0 is an image of this 0. This negative 0.7923 is an image of this, and then this one. So they can be mapped to each other. Now you may be wondering, what about a graph with odd number of vertices? So that's what I have shown here, and these are the eigenvalues that are shown for this graph. So again, you can have mirror image. So for negative 0.5463, you have positive 0.5463. Negative 0.9999, you have positive 0.9999. It's only for the 0 you don't have an image, but it is standing in between the two, the negative values and positive values. So that's what you would expect to see for the eigenvalues for a graph with odd number of vertices. You will have a 0 in between. It will definitely have a 0 as one of the eigenvalues, and above that will have all the negative eigenvalues and then the positive eigenvalues. Okay. Any question on all these things?
Dr. Man, I just got lost in some point when you calculate the effectiveness of. So you calculate the index for part of the graph only, or?
No, you calculate it for the entire graph. So let me go back.
Yeah.
So given a graph like this. What we want to calculate is the folding effectiveness. It means how folded is this protein with all these nodes considered as amino acid. You have complete folding if you have a complete graph like this. It means there's a link between any two nodes which are amino acid. Okay. Now the other extreme you could visualize is something like a chain. This is a minimum. You need to have a connected protein. So this is not at all good folding. Okay, whereas this is the best possible folding we could have. So what we want to capture is, given a graph like this, where is this standing in between these two extreme cases? So if the given graph is also is also a complete graph, then you're going to have the ratio turning out to be 1, right? Because if this given graph has 5 vertices, so once you know that it has 5 vertices, you can draw a complete graph by yourself. I need not give you this graph, because this is a complete graph. That means every vertex is going to be connected to every other vertex. That's all. It's a complete graph. So all you need to know is how many vertices are there in the given graph. Once you know that, you can draw a complete graph like this, then generate this adjacency list, feed it to the spectral analysis code, and can compute the eigenvalues, e to the power of those eigenvalues, sum them up. So once you know the number of vertices in a given graph, you could get the Estrada index for a complete graph with the same number of vertices. Then for the actual graph, go ahead with the same process of computing the eigenvalues and e to the power lambda eigenvalues and sum them up. That's the Estrada index for the given graph. That's the raw graph. Okay. Then just take the ratio of these two numbers. So this is what you got for this graph. Then for the complete graph, this is the number you got, and this is 0.385. And to make your understanding even better, you see this is a different graph of 5 vertices. So this is some other protein. And you go through the process of computing its eigenvalues and the lambda and e to the power lambda values and sum them up. So you get 16.51. But the complete graph for this graph is also going to be the same graph here, because all you need is the number of vertices. So this graph also has 5 vertices. So any 5 vertex graph is going to have a complete graph like this, and an Estrada index as this value. So it means you could divide the Estrada index value that you got for this actual graph by the Estrada index for a complete graph, which is same number, 56.048, and you get this ratio. So now if someone tells me that the folding effectiveness for this graph is 0.385 and for this graph is 0.295, I can kind of interpret the two numbers and say, okay, this graph is relatively less folded, and I can kind of have a feeling of how less folded is compared to this graph. So this one is 0.385 and this one is 0.295. On the other hand, if someone has given you this graph and you do this analysis and come out with 0.187, now you have a kind of feeling of, okay, given these three graphs with these numbers, you have a sense of, okay, how folded is the graph. You see what I mean? Is that clear?
Okay. Yeah, it's clear. Yeah, just the denominator, all of this has the same value, so it only depends on the number of the vertices, right?
The denominator, which is based on the number of vertices, because that's for a complete graph of these of those five vertices. All these graphs, just for comparison, I took the same number of vertices, but you see the structure, the topology is different. This graph has this distribution of edges, this has different.
Yeah.
So they are all different graphs. So what we are trying to find is how folded are these graphs. And by folded, in our graph theory context, it means how close is that to a complete graph.
Okay.
Okay, so with these numbers, so that's what we are actually trying to find. If you are given a graph that is complete graph like this, let's say you are given this graph, you would go through the calculations and come up with this raw Estrada index. And the complete graph for this graph is also same graph, because all you need to get a complete graph is just number of vertices, and then you can draw edges between any two vertices and get a complete graph. So that means the ratio will be 1, because 56.048 is the Estrada index for your graph divided by the Estrada index for a complete graph of the same number of vertices is going to be the same value, so it's going to be 1. So that's what you would expect, the best possible folding effectiveness. But for any real world graph like this, you cannot expect everything to be completely folded like that. You will get some ratios less than 1, and those are these numbers.
Yeah, okay. Yeah, that's clear. Thank you.
It's clear now? Okay, good. Okay, let me see what time is that. Okay, so let's do this. So let me save this video first on Estrada Index.